Hi, hi guys, welcome to the lesson of partial differential equations. So in our previous classes, we discussed integral curves, formation of PDEs, and Cauchy characteristic method for linear PDEs, then semi-linear, quasi-linear, and then nonlinear PDEs. So now in this class, we are going to discuss Charpit's method for solving partial differential equations. So the basic idea of the Charpit method is that if a partial differential equation is given, so we have some conditions that are dx over negative fp is equals to dy over negative fq is equals to dz over negative p times fp minus q times fq is equals to dp over fx plus pfz is equals to dq over fy plus qfz. So you guys are familiar with this stuff, fp, fq, this and this. If you remember, we use these in the Cauchy characteristic method for nonlinear partial differential equations, where we said that dx over dt is equals to fp, dy over dt is equals to fq, dz over dt is equals to p times fp plus q times fq, and then dp over dt is equals to negative fx plus pfz, then dq over dt is equals to negative fy plus qfz. So we use these conditions in the Cauchy's characteristic method for solving nonlinear differential equations. So this is almost a similar method, but we are not dealing with the initial value problems here. We just need a general solution for a given PDE. So the other condition we have to use, the first thing is that we have to use a couple of these equations, and we have to find p in terms of x, y, z, and q in terms of x, y, z. That is our objective. And then we have to apply this equation, dz is equals to p times dx plus q times dy. And then we will solve this equation for a function z in terms of f, x and y. So just for recap is that when we are given with a function that is f is equals to some function of p, q, x, y, z, that will be an equation of nonlinear partial differential equation. So if we are given with this equation, first thing we need to do is we have to find fp, fq, then this, and this, and then we will apply these to this system of these differential equations, and then we will pick a couple from here which we can solve easily, and we will solve for p and q. Then we will plug that p and q in this equation. Say this is equation number 2, and this is equation number 1. So first we will use equation number 1 to find p and q in terms of x, y, and z. Then we will apply that p and q in equation number 2, and we will solve for the general solution. So let's start with an example. Let's say we are given with a question says that p times x plus q times y is equals to pq. Now you guys are familiar with these types of equations. We can see that this is a nonlinear PDE because here the derivatives p and q are in the product form. So this is a nonlinear PDE. So now we'll apply Charpit's method and we will see how to solve using Charpit's method step by step. So first thing is to write this equation in terms of a function that is px plus qy minus pq. So I just place this pq on the left hand side and write it in form of the function because it's a function of p, q, x, y, and z. So the second thing we have to do is now we have to find first of all fx, then fy, then fz, then fp, and fq. So fx will be the partial derivative of this function with respect to x. So fx will be equals to p. Then fy will be the partial derivative with respect to y. So it will be q because here it's the derivative of px will be 0 with respect to y, and then with respect to y that this derivative will be q only, and then this will also be 0. So fz will be equals to 0 because there is no function of z here. All will be 0 when we apply the derivative with respect to z. Then fp will be equals to, here it will be x, and here it will be negative q, so x minus q, and then fq will be equals to negative p plus y. Now you see we found all fx, fy, fz, fp, and fq. So now we'll apply these to the equation number 1, which we the general equation which we call as equation number 1 above. So we will apply this. So we said that it's d over negative fx. So it will be negative p sorry, it's dx over fp, not fx, it's dx over fp. So what's our fp? Fp is just x minus q. So negative x minus q is equals to dy over fq. So negative y minus p is equals to dz over p times fp. So p times fp is x minus q. Negative sign will also be there, and q times fq, that is y minus p. That will be equals to dp over fx plus pf z. So fx is p and fz is 0. So p multiplied by fz will be 0. And again dq over fy plus q times fz. So fz is again 0. So we will only left with the fy, that is q. So now we have to use a couple of equations from this system of ODEs. And first of all, when we see this equation, this is dx over negative x minus q. So this equation seems not separable because q is also there with x, and when I want to use this equation with some other function, so it's difficult to use this. And then if you look at this equation, this is also negative y minus p. It's also difficult to solve. This also difficult to solve because a lot of variables are involved here. But these equations we can see are the simplest equations, that is dp over p and dq over q. So we can take the couple and we can solve this equation simply by integrating. So this implies that ln p is equals to ln q minus ln c. So if you want to apply the property of log, so we can write it as p is equals to c times q. So it's all good up till now. Now we will proceed further, and remember our goal is to find the p and q in terms of x, y, and z. So still we have only found a relation between p and q, so we need some more relations. So if I plug this p in equation that is given, that is the f, which is f, that is f is equals to px plus qy, that is the original equation, is equals to 0. And now I can plug cq instead of p in this equation. So this implies that cq times x plus qy minus cq times q is equals to 0. So now we apply this to the equation that is the given differential equation. We just replace cq in place of p. So now we can write it as cqx plus qy minus cq squared is equals to 0. So I can take q as common here. So I will left with cx plus y and then cq squared. So this squared will be cancelled with this q. So I will left with cx plus y is equals to cq. Now you can see that cx plus y over c is equals to q. So we found q in terms of x and y. So now we have to find p in terms of x and y. So what we will do is we will use the equation p is equals to cq again. P is equals to cq, and we will plug this cx plus y over c in place of this q. So we'll find p in terms of x and y. So it will be c times cx plus y over c. C and c will cancel out, so we're left with cx plus y. So now p is equals to cx plus y, and q is equals to cx plus y over c. So now we can see that we found p and q in terms of purely x, y, and z, where we have only x and y here, but this doesn't matter. We can only have x, y, and z, no other thing. So now we will use this equation dz is equals to p times dx plus q times dy. So we will apply this p here, that is cx plus y times dx plus then q is cx plus y over c times dy. So now I can multiply the whole equation by c to just get rid of c from here. So it will be c times dz is equals to c times cx plus y dx plus cx plus y into dy. So now if I take cx plus y as common from right hand side, so I will left with c dx inside plus dy. So now I can see that this cx plus y is basically the derivative of this function, this c dx plus dy. When I will uh, apply the integral, so I'll only left with, like, if you want to write it like this, c, now for simplification, I'm multiplying to make it easier for understanding. I'm multiplying this with this, so I will get c squared x dx plus cx dy plus cy dx plus y dy. So now this and this is easily integratable, but for this equation, we will write this in terms of an exact differential equation. So if I take c and c common, I will left with x dy plus y dx plus y dy. Now c squared x dx plus c times. Now this is nothing but d of xy. Now all the equations are, all the terms are integratable, and so we can integrate it easily. So this will be c times z. This will be c squared x squared over 2 plus this will be c times xy, because this d, that is showing that this is the derivative and this is the antiderivative, this integral sign. So this will cancel out and we'll only left with cxy plus y squared over 2. So now we almost are done with the job. So we can write it like that: c squared x squared over 2c. I am just dividing this whole equation by c to get rid of c from here, and I will free this z from any other variable. So this will be c times x y over c plus y squared over 2c. So z will be equals to c x squared over 2 plus xy plus y squared over 2c. So this is our final answer. And our goal was that we have to find a function in terms of x and y, that is z is function of x and y, and we can see here the z is function of x and y. So hope you guys understand this question. So let's take another example in order to consolidate the concepts. So let's say we are given with a equation, question number 2. Let's say we are given 2z plus p squared plus qy plus 2y squared is equals to 0. So now the first thing is that we have to write this equation in terms of a function f. So it will be easier for us to find the partial derivatives. Like we have to find fx. So fx will be 0 because there is no function of x here. So fx will be simply 0. Then fy. So when we will partially differentiate this with respect to y, this will be 0, this will be 0, and here we will left with q, and here we will be left with 4y. Then we will differentiate partially with respect to z, so we're left with 2 only. Then we will do with respect to p, and we will left with 2p only. Then we will do with respect to q, and we will be left with y only. So we are done with the derivatives. Now we will apply the equation, that is dx over negative fp is equals to dy over negative fq is equals to dz over negative pfp minus qfq is equals to dp over fx plus pfz is equals to dq over fy plus qfz. So now we'll plug the values. So fp is nothing but it's equals to 2p, so it will be negative 2p dy over negative fq, and fq is equals to, we can see here what's fq is equals to y, so it will be dy over negative y dz over negative p times fp, that is negative 2p, minus q times fq, that is negative y, is equals to dp over fx. Fx is 0, so 0 plus p times fz. Fz is 2, and dq over fy. Fy is q plus 4y plus q times fz, so q times 2. So now we have to take a pair from this system, and we have to choose such a pair that we can easily solve by using variable separable method. So here we can see that if we choose this equation, with this equation we can solve it easily, because it's dx over negative 2p, and that is equals to dp over 2p. So this will cancel out, and this will implies that negative dx is equals to dp. So now we can easily integrate this equation. So we will get negative x plus a is equals to p, where a is the constant of integration. So we're left with p plus x is equals to a. So now I found the function of p in terms of x and y. So I can say that I have found a function of p in terms of x only. Then now I can plug this in the original equation in place of p. So let's do that. Plus a minus x squared plus q times y plus 2y squared is equals to 0. So on simplifying this, I need an equation in terms of x, y, and z for q. So I will isolate this q, and I can write it as negative qy, and then q will be equals to negative 2z minus a minus x squared minus 2y squared whole divided by y. So now this is a function of x and y on the right hand side. So we found q as a function of x and y. Now the next step, now we found p as a function of x, y, but it's only function of x. That's okay, it's good. Then q is the function of x and y. It's good. So now we can apply the condition that is dz is equals to p dx. That is dz is equals to p dx plus q dy. So we can use this. So I will write a minus x in place of p because I found p as a minus x, and then the whole function that was negative 2z minus a minus x squared plus 2y squared. Sorry, it's minus 2y squared, not plus. It's minus 2y squared divided by y and dy. So now if I see here, I can just simplify this equation by multiplying and divide. So now I can add y dy here, and sorry, y squared dy here, and y squared dy on the right hand side. I will take this minus sign out of the bracket and here to the plus. And or I can just say that it will be confusing. That's why I'm removing this. Now I will just do one more step. So here it's 2y squared. So I want to shift 1y squared from here. So how can I do that? Because it's divided by y. So if I can break this in like y squared plus y squared. So let's do one more step. It's okay. Let's do one more step just to avoid confusion. So dz minus, now I'm shifting this to the left hand side, and now I will be left with, so I can write it like this: 2z over y plus a minus x squared over y plus y squared over y plus y squared over y. Why I am doing this? So you will get the idea further when you will get too close to the answer. So you will get the answer why I am doing this. So now I can take this one of this y squared over y with dy to the left hand side like this. Simplification for simplification. So it will be minus y squared over y dy. So I will left with only 2z over y plus a minus x squared over y plus y squared. It's It's not 2, it's y. I'm very sorry, it's messy, I know, but this question is like that. It's somehow confusing. So this y will be cancelled out with this y. So I will left with dz minus a minus x times dx minus y dy. So now you can see that this will be equal. So now I am taking y as LCM again just to make one equation. So I will do that plus y. So it will be y squared, sorry. So now you can see that here it's z and here it's 2z, here it's dy also, I'm sorry. So now I will shift this equation to the division on the left hand side. So I'm writing it like this: 2z plus a minus x whole squared plus actually this was positive y because here it was negative sign, and when I remove this y squared over y with negative sign to the left hand side, it will be positive y. Okay, so this was positive. I'm really sorry. This was positive, and this will be 2z plus a negative x whole squared plus y squared is equals to negative 1 over y dy. What I did is I pick this whole equation, this upper part, and put it to the denominator of the left hand side. Now I can see that here is the z, 2z, and here's dz. So I need to here to make it the perfect derivative, and here's a minus x whole squared. So the derivative is 2 multiplied by a minus x multiplied by minus 1, that is 2 multiplied by a minus x. So I need 2 here again, and here's y squared, the derivative of y squared, it's 2y, so I need 2 again. So when I multiply this equation by 2 on the numerator, so I will apply by here on the denominator also. So now the numerator is a perfect derivative of the denominator. So now I will conclude this: 2z plus a minus x squared plus y squared, and I will shift this 2 to the right hand side, so it will be negative 2 over y dy. So now this is a perfect total differential equation. So I can take the natural log of this equation, 2z plus a minus x whole squared. I will repeat this again, that this whole denominator is the derivative of the numerator. Okay, so like when we have dx over x, we integrate and we take ln x, because this the derivative of x is what here, dx. So here it's 2z, and the derivative of 2z is 2dz, then plus a minus x whole squared, so its derivative will be 2 multiplied by a minus x multiplied by minus 1. So this minus 2 multiplied by a minus x dx here, plus then for 2 y squared, it will be 2y dy, and here it will be minus 2 ln y plus ln c1, we can call it ln c1. So now the general function is we can just simplify using the properties of log. So it will be c1 over y squared Why? Because this negative 2 will be come to the power of y, and sorry, it will be this y power minus 2 because it's y minus 2. So I can write it as c1 y squared. So now the last step is that here it's ln. I forgot to write the ln. When I will take exponential, so this ln will be cancelled and I will left with 2z plus a minus x whole squared plus y squared is equals to c1y squared. So you can simplify it to find z in terms of x and y using one more step, and this is the answer. Or you can leave it like this also. So this is the final answer, and hope you guys will understood it's a difficult topic. But if you will do practice more and more, you can like be good in this topic. So you can practice one or two problems to make your concepts more stronger. And thanks for watching the video.